today, I want to, in some sense, share with you some ideas. So probably not only satisfactory for someone, but while somehow can understand that it's a little bit far for its fields of interest, but my goal is to share this idea about what. So biological neural networks, artificial networks. Okay, looking for the best from both. What I mean. So you know that the very, very huge goal, grand challenge is to understand the human brain. Okay, it's a very, very great challenge. And in some sense, how to the brain becomes a mind. It's a very old as a human problem, and I don't want to solve this problem, but I only to understand if it's possible to, in some sense, go together from artificial and biological ideas. So, biological or artificial networks, which is the problem? Okay, it's not a problem because instead of or, I think is and, because I want to understand if it's possible to take some idea from signal processing, for example, and artificial neural networks together with some ideas, or if you want, some data, some reality from biological networks. And look also to something rich related to our project between India and Italy is about robotics. And I am not an expert in robotics. And at the end of the day, I want to show you some surrogate where you mix biological and artificial networks in order to have a very efficient, if you want, is my hope, and low power consuming device in order to control, for example, a robot or something like that. So this is my outline, but probably I will not touch all the points. And you know, it's possible to understand, to study, to have some idea and some hypotheses about the brain by using the different approach. So the multi-level approach, what means? Okay, it's possible to have a multi-level approach, but it's possible to have top-down or bottom-up approach. What means? Means that depends on your data and depends what you want to understand, what you study, what you use, where you put your eyes. So, in a bottom-up approach, this is from some slide of my colleagues also involved in the project, Giglio D'Angelo, Professor Giglio D'Angelo, and you start for a very basic biological facts, genome, something like that, and synapse, and so on and so forth, your neurons, and local networks, and reach the behavior, okay? And this is a bottom-up. And also, it's possible to have a different approach with different time scale and spatial scales. Probably Michele Migliore showed you something like that about the hippocampus. And you have different time scale and different spatial scales. Okay, this is one possibilities. And in a real world, you start from a very macroscopic aspect and go with the neurons to the networks to the behavior. This is one of my charts, okay? And also now interaction between humans, for example, and the interaction with the environment, okay? So this is a bottom-up approach, and there is a pro and contra about this approach, and in a classical reductionist approach, we have some data. Okay, but in some sense, we have a basic brick. For example, neuron. You fix the scale of neuron, but with a brick, it's possible to have only a group of bricks, or it's possible to build some wall. It's possible to build some very beautiful cathedral. It's possible to build a house. It's possible to do anything. So the organizations between the bricks or if you want, the functionality of the bricks, not only as a single bricks, but also as a group with some functions. It's possible to obtain something. It's possible to obtain some information from a single brick, but you have to add something, okay? For example, for the neurons, it's possible to add not only the local data, if you want, from some experiments, but also how it is organized. What is the network? What is the functionality of the networks? Okay, and here is a slide I use also when I'm teaching, because in some sense is how, where, and who of the, and what, and why, and when for the neuronal processes. Okay, it's possible to simplify, roughly speaking, in a three main scale. So by microscopic scale is very clear because it's from molecules, for example, and the mesoscopic scale where we have some local circuit for, and macroscopic scale where we have some fields model, the whole brain of something which is at the very, very macroscopic space with respect to microscopic scales. Okay, and how to go from one scale to another scale. There is different approach. For example, macroscopic scale at the level of neurosomal synapses, and want to go to macroscopic scale is very, you need a very, very huge computational force, okay? And usually you have to use some mean fields, some mean fields approach, okay? And in film models, in mean field models, you, in some sense, you have some informations, but you lost the microscopic or microscopic details. Okay, depends what you want to describe. And otherwise, in macroscopic picture, it's possible to see something, and it's possible to compare with some data, for example, from MRI or something like that. So we have different scale, different data, with different approach, and it's possible to have different things. Okay, you know, our main object is the cerebellum, okay? And also is related to the movement, but not only to the movement, because recently, also in our project, it's possible to relate the cerebellum to some diseases, neurodegenerative diseases, for example, and it's Alzheimer's, Parkinson's, something like that. And also it's possible to consider some rare diseases as ataxia or something related to the normal movement for one human. Okay, so there is different reason to approach, to model the cerebellum, to understand how the cerebellum is involved in different things. Okay, and for us, I have a very restricted window, if you want, because you consider something related to the movement. Okay, and this is one very beautiful picture, and it's possible to recognize again the multi-scale organizations. And okay, there is, for example, if you want to describe a mathematical way in a formal way from the data, for example, this is a typical system of ordinary differential equation in order to describe the main quantities for one neurons. And here is not important to see what you write, but there is an ODE system in order to describe, for example, the so-called the dense or ionic through the membrane of a neuron in order to describe the spiking activity of one neuron. And also it's possible to describe with some Markov change, or we describe with some ordinary differential equation, also the dynamics of synapses. Okay, well, formally, from a mathematical point of view, at the microscopic scale, or if you want, not so microscopic, but in some sense, using ordinary differential equation in some sense is some kind of mean field, because microscopy means to go to the particles, something like that. Here we have some population of ionic channels, and we have, in some sense, at that scale, it's possible to have some mean field described by ordinary differential equations. And Ordinary differential equation depends only to the time. So there is also the space. And you have to organize in a network this model. And it's possible to understand that you obtain a huge amount of ordinary differential equations and something like that. Okay, from the computational point of view, it's possible to build using some approach this kind of computations, but it's very time consuming. It's very you need a very power for the computations. Okay, and for the top-down brain modeling, we start from macro scales, from the data for MRI, something like that, and try to understand as an inverse problem, to understand, to verify, or you understand which kind of phenomena appears at macroscopic scales. Oh, okay, but warning is an inverse problem. As an inverse problem is the eye conditional problems. Means that for eye conditional problems, that, for example, it's not possible to have, you need some stabilization algorithms because you have not, for example, uniqueness, we have not, the data depends not in a continuous way from the model, something like that. So the eye conditional problem. So inverse problem could be interest, but it's very difficult because you need some sophisticated tool in order to understand, to certify the uncertain inside the process to inversions, okay? And here is a slide from a colleague in Munster and about the large scale picture for multi-scale inverse problems. It's very difficult problems, okay? And we want to derive reduced macroscopic or multi-scale models in efficient numerical solutions. But you need a huge amount of data. It's a low sensitivity for identification design variables with respect to the data, and the simulation data require many solution forward model. So you need to many computational solution, or if you have many simulation, numerical simulation of a forward problem. Okay, and this is a problem because you need high computational effort. And also we need some kind of optimization problems, least square, classical least square, or some optimal design in order to match the microscopic data and the microscopic model, okay? So we need a sophisticated optimization models. Also, probably it could be a problem. So the top-down is useful, but inverse problems. We need a lot of things. Okay. What is my approach in the last time? So some topics. If you want to use bottom up, or if you want to use top down, if you want to solve an inverse problem, or if you want to go from basic bricks to the wall, okay? And you need a reduced model. And for large neural network simulations, you have to lose some details because you need a very high performance computing. And modeling synapse, okay, because you need to simulate a network. What is neural code? Okay, also here there is a fight between, okay, I want to ray code. Ray code is a right code, or temporal code. Temporal code is a right code. Okay, it is a possibility, but for me is and. Probably there is some rate and temporal code that we go together. And moreover, you have different neural populations and also to realize a mean field approach. Or Fokker-Planck equation for statistical physics, integral equation, multilayer network. So all that is about the heterogeneity of the neural populations, and they want to describe with a few parameters the macroscopic world. And in order to have a less computational cost, and also you have to meet the macroscopic data at some intermediate scale. Okay. There is an approach, I think is very natural, but also recently I found in some paper where the sentence here is from IEEE papers in a proceedings is a composite neural networks. It's very natural. It's a stupid if you want observations or if you want reverse observation is especially suitable for build a large-scale heterogeneous neural networks. What is the idea? It's a natural idea. So instead to have only a very large, unique and heterogeneous network, you, in some sense, split in different small scales, microcircuits, and try to train individually the microcircuit. Okay? This is a very simple idea. And how to apply, for example, to cerebellum. And cerebellum, for example, in an input stage where we have a granular layer and the Golgi cell, which project also both to Purkinje cell, it's possible to have, for example, two different networks, one from granular Golgi cell and then a Purkinje cell. How? I want to explain what is my idea, starting from this very, very natural idea about to splitting in a different microcircuit, but not by using the mean field, by using the network, okay? I don't want to use the mean field approach, but want to, in some sense, hold some feature of the networks. Okay, and it's possible to consider also this approach for neurorobotics or for some neuromorphic device. Why? Because in neuromorphic device, my colleagues told me that okay, you have to have not so detailed models, and you want to in some sense to develop some surrogate about the real neuron, because it's very using a new material, new device, possible to have very efficient, fast, and very good neuromorphic device. And okay, how to go from the biological world to artificial world? Okay, this is now my recent. There is now I propose you an approach. It's not my approach, but it's an old approach also. And for example, if you want to simulate something by using the fashions, the neural deep learning networks, okay, you have some problem because you have to train with training can be slow. You need a lot of data. Now, there is also the problem to have very high quality data and the convergence for optimal solution because you have to involve some optimization problem is not guaranteed. I'm very surprised because in some deep learning networks, there is an optimization tools, which is called ADAM techniques, but from a mathematical point of view, we, in some sense, we prove that this algorithm does not converge to optimal solutions in many situations. But it is used in the community of deep learning networks. I'm very surprised, but what means that probably you this very nice optimal solution, but it's possible to have some almost optimal solution is enough or something like that. For me, it's very surprising, but for my mathematical community, because okay, we have Adam algorithm, but Adam does not converge in many situations. Why do you want to use? And also you have energy consumption with a very, very, very deep learning large learning networks. Moreover, there is results about the possibility to have a neural network, for example, deep neural networks forward neural networks in order to represent a very complex process. Because there is some, if you want, in some sense, negative results. This is one example of 2 years ago, where, okay, here I translate in some sense in words the results. Oh, okay, so there is some well-conditioned problems. So we look not at all conditional problem, some scientific well-conditional problems and it's possible to prove that exists a neural network which is in some sense stable for that problems. Okay, but it also is possible to prove for someone is surprising, it's not possible to have an algorithm, okay, such that it's possible to design this neural network with high accuracy. So it's possible to prove that, oh, for this problem exists a neural network for with some layer, okay. It's possible to solve in a stable way by using neural networks this problem, which is wild conditional problems, not high conditional, wild conditional problems. For example, a simulation of something. Okay, but for it's possible also to prove that exists problem and it's not possible to really compute with accuracies with networks. Seems very paradox, but is theoretical results, recent theoretical results. And the problem is, if you consider a scientific computing problem, and they want to approach your neural network, you are not sure that a good algorithm, where good means accuracy algorithm, exists. And for some cases, possible to prove, but you need some works, for example, for using, in a typical example, for considering the denoising on some image processing for MRI. It's possible to have a stable accuracy neural networks. Okay, as some mathematical results is existence results. Okay, and it's not constructive results. And repeat, this does mean that for your problem, it's not possible to have a very accurate network, but could be. Okay, and is a mathematical result. So now Now, I consider also for neurorobotics applications some reservoir computing setting. I don't know if it's the reservoir computing setting, but for me, it's a surprise. But you have first, you introduce the time. And this is important for us because for granular layer, there is also time is very important and is one of the main properties about granular layers. The two properties from granular layer is, or if you are you become the signal in input becomes sparse in some sense, and there is a timing. Why? Because timing is very important in order to have a coordination of the movement and the control of the movements. Okay, you need some, in some sense, coordinations. Here, there is a time. So suppose that in the input, you have some serial data from some dynamical system. In a couple of slides, I show you some very typical example of that. And then you have a reservoir, which is represented by a network or recurrent neural networks. But now the weight in the connection are fixed, are random from some distribution, usually Gaussian distributions, and fixed. Okay, so nothing to train. The only things to train is the output. The readout has to train, but is a linear, in some sense, a linear object to train in a very fast way. So it's possible to use something like that. For me, it's a surprise. Probably for some our in audience here is a clear things, but you have a high-dimensional dynamical system with random weights fixed, and you have only to read out to train. Okay, and one thing is for me is a very useful surrogate in order to go from biological network to artificial networks, and because it's possible to classify the pattern in input, for example, for some sensors and or some from dynamical system, and to possible to classify in a very efficient way. Okay, there is some hypothesis about the random weights, but I want to go to the mathematical details. For people interested, one main property is about the spec is to represent the connection with some metrics where the entry of the matrix are weight, and it's possible to have some hypothesis about the spectral radius of these metrics, but it's a mathematical details. Okay, and this is a typical examples. You have some ground truth which represent by dynamics. Supposed to simulate here, and in reality, you have some data from dynamical system or some data from some sensors. Okay, and then you put inside this strange traditional reservoir computer, and then it's possible to train in order to forecast the dynamics. So I don't know the equation for dynamical system, but it's possible to forecast, reproduce the dynamics. Okay, and roughly speaking. So okay, I don't know the details. This is the idea. So. What is it to be learned? Is this matrix here, and you collect with respect to the time series, go to the reservoir, the state of the reservoir depends on the what. Look here, depends on the actual state, which is, for example, something in the nodes, and the actual inputs, and with some noise here represented by vector B, and we have some convex sum between two terms, which is the actual state and the updated state. So this is the in the discrete time phase for traditional reservoir computer. Okay, one example here is a chaotic component for the chaotic dynamical system. So a chaotic, so there is not, is very difficult to, you have not have equation here, so you know the equation, but because you have performed some simulated data here, and use as f of x because some non-linearity has to be involved in the process. The non-linearity is here, and look, you have some reservoir, and then go inside for some sample. We use some sample here. For example, the original signal, the original simulation is about 10,000 of samples, and here trained uh, uh, um, uh, some sample. If I will remember, in these simulations, I take for training 1,000 of samples. So we expect to, so I use a 20% of data in order to understand what is the, in order to forecast the dynamical system and input. Okay, there is some reservoir activation, so there is a dynamics at some node, and here is the comparison between the original signal, and here in green is the simulated, if you want the training signal. Okay, so there is some error. Okay, and here you use as a non-linearities the hyperbolic tangents, but I want to change this non-linearity. For example, here is the weight in the output. So what is the idea? The idea is to embed the original dynamical system, which we read about, we read not the equation, but we read the time series produced by dynamical system, and repeat in reality could be some measure in the environment or something like that, and then try to understand, is possible to classify or in pattern, or is it possible to have some forecast about these signals? And here is the results about the only weight in the readout to be trained. Okay, this is a comparison. And if you, I want to, for example, change the nonlinearity. If you change the nonlinearity, more or less, if you compute the mean square error between the original signal and forecast signal, you obtain something which is comparable. So seems in these experiments that the nonlinearity is not so important. Okay, but and then there is some activity in the node. Here, the magnitude of the forecast signal is okay. We train something, but seems that some shift appears. Okay, also change the use the sigmoidal function here. And again, if you compute mean square error, we have something is comparable. But now, after some time, so you have something which is very, very similar, very close to the original dynamical system, dynamical data, but there is some also shift here. Okay, it's only an experiment. And for all cases, I change only the nonlinearity inside the model, but the connection, which are sparse connection, are the same. So same random connections in the reservoir, okay, and then seeing only the nonlinearity. More or less seems that nonlinearities linear, if you change linearities, more or less you obtain something which is the same results. Okay, but now, okay, we study biology, we take experiments, we have macro data, micro data, something like that. Where is the biology? Okay, okay. It's possible to introduce something which represent more from a biological point of view, more related to the biology. For example, instead of a discrete time, you use the time, the continuous time, instead of a discrete state, if you want, you have to obtain something which is related to a system of differential equations, as in a classical model for neurons, okay? But it's not so classical here because we have only some very few parameters. Okay, similar networks appears in many, many, many situations. Okay, and look here, and again, we have some connection, and again, we have some random fixed recurrent connections, and but now the dynamics is described in each node by using a differential equation. Okay, and also, what is the unknown? Where to want to train? We train with weight in the readout. Okay, good. One remark: it's possible to use this kind of things for multitasking because it's possible to have the same input, for example, and the same reservoir computer here. And then it's possible to extract different readout, and it's possible to train different readout based on the same reservoir and the same senior here. It's very interesting also to have a multitasking things. Okay. It's possible to have also some, if you want, approximation theorem, universal approximation theorem as for classical results for neural networks, but using differential equation. Here is not exactly the same as before, but I skim some mathematical details, only the idea. It's possible to use theorem as reported here for Funashi and Nakamura, in 93, but it's possible to that results as these results and say, okay, if you have an autonomous ordinary differential equations, it's possible to map, it's possible to have a reservoir which in some sense describe with some accuracy the original flow. So here is the results. It's a flow of original dynamical system, which I don't know. It's possible to have only the flow of a system. In reality, we have some measure plus some noise. And here is the reproduces flow of a reservoir. So is this some universal approximation results as in typical neural network set frameworks? Okay, but now what is the idea? The idea is the old idea for Jaeger, Mass, and some other guy here. And but now I want to introduce more biological property in the reservoir. So I want to show you only one example because it's a work in progress. And for example, what is the goal? Now, I want to describe, I want to, in some sense, obtain some constraint on the reservoir, okay, but in order to hold some biological requirement. For example, synchronization. I want to reservoir which is able to synchronize in some sense. For example, my idea for a granular layer is the following. Uh, for the input for MOSI fiber, project to more or less 50 granular cells, and then exists a clock inside the circuit. Yes, it's a Golgi cell. So the idea is the following. It's possible to have a synchronization inside a reservoir. And if yes, what is the minimal hypothesis in order to have a reservoir with synchronizations? So it's a typical, okay, here is a typical video where it's possible to have synchronizations. And here is a classical video movie where we have some metronome with some clock, and then we start with no synchronizations. But after some times, it's possible to reproduce the same experiment. Is a lot of metronomes, and it's possible to have, if you want to wait sometimes, and after some times, we have a whole synchronization of our systems. Okay, where is the tricks? The tricks is under. Why? Because the tricks is the can of beer, because it's possible to observe that the connections is in direct connection by using, in some sense, this plane. And after some times, all clocks are connected in some sense using the elastic energy produced by this movement of a can under the plane, the can of beer under the plane, okay? And then means that all the clocks speaks with all over. So is a one-to-all connections, okay? Also is a bidirectional connections. Okay, it's possible to model something like that by using a classical system. For example, in physics, it is a Kuramoto's model. Okay, it's a toy model, but it's possible to understand here there is some oscillation represented by sinus functions. And here is, in some sense, it's possible to think as a particle with different angular velocity, and we adapt the velocity in order to have a synchronizations. Okay, in a capital K is the strength of the connections, and divide by the number of particles here because we need some normalizations. Sorry. And now it's possible to understand what is the asymptotic behavior of the system. And my observation is, in some sense, Kuramoto model is a special case of recent Cooker-Smale model where we have not angular velocity, but you have some Cooker-Smale is a model in order to justify to describe in a phenomenological way the flocking of the animals, for example, or something like the formation of a crystal, something like that. So it's possible to use the Cooker-Smale theory. Also, yeah, skip some details in order to understand what is the hypothesis for synchronizations. Okay, what means synchronization? So the complete phase synchronizations means that asymptotically we have a difference between two different angular positions is equal to 0. So synchronize, all particles are overlapped. So also it's possible to have a complete frequency synchronizations and look to the frequencies instead of the angular. So it's possible to prove that under some hypothesis, it's possible to have complete phase or frequency synchronizations, okay? By using the Cooker-Smale. So Now, I want to introduce this constraint, this hypothesis in order to have a synchronizations, okay? Some people follow the analogous idea also for synchronization of subgroups inside the system. And what is the problem? The problem is that the graph represented the Kuramoto dynamics is a complete graph. It's possible to have a connection between any different nodes, but this is not very logical. So, and moreover, I want to use the sparse connections. Okay, in our reservoir, you want to use sparsity. Why? Because also in granular area, they promote the sparsities. Okay, so how to proceed? This is some experiments about how the connection, if you want, the topology of the connection can influence in some sense the dynamics. This is a experiments in Genova, but I want to skip that and look here. And we have, for example, some results as the following. And you have here is starting from the experiment. Now you have some simulation by instance introduces some randomness inside the connections, in the matrix of the connections. And here is a simulation, and look here, if here is a pattern network, but you have no synchronizations. Here you have more synchronization, and here you have complete synchronization, or if you want, acceptable synchronizations, and depends on the topology. So different topology promote or not synchronization inside the system. And if you want, study something like that, some meta theorem is if you want to have a synchronization in your reservoir, you have to consider unidirectional connections. So my matrix is not symmetric. It is different with previous theory of reservoir. We consider the probability of firing, so it be possible to consider weakly firing neurons and consider probability of firing depends on synaptic inputs in some way. You have need some energy, some background noise. You need a noise, and you need some delay in the communications. Moreover, you need some also, in some sense, not only local connection, but with some long connections. Okay. And also, finally, the hypothesis after firing, the neuron remains silent for some times. So this is some basic hypothesis in order to have some synchronization. So the problem is now, okay, I want to compute, I want to have some reservoir with synchronized. So I want to introduce this constraint in our reservoir. So it's not random weights, but you have to select some sparse connections with also some long connections, some probability to have a long connection with two nodes. And you have also some constraint about the delay inside the nodes. Okay, and also you have some hypotheses about our system. So this is more biological inspired. Okay. Okay, so there is some simulations, and this is our next work is to simulate by using reservoir biologically inspired synchronization, some granular layer, for example, and okay, and I think my time is ended. Okay, and okay. And I can stop here. Uh, mm, and I hope that I try to sketch our idea. The idea is I summing up to have some reservoir computing, but introducing some biologically inspired constraint inside. And in order to reach different goal, in order to have a very, very efficient things as a surrogate for dynamics, and then also to have some biological inspired reservoir. Okay, I try to do that. Okay, thank you. Sorry for, because now I have something like that for the connections. So summing up, okay, our goal is to describe something like that, okay, by using this idea. Okay, thank you for your attention. So there is a question in the chat. So we can consider the dynamics function used in reservoir for the activation function also. Okay. Uh, uh, here, it's not so clear for also to, not the question is clear, but it's not so clear for me. I mean, there is like to use something for artificial, uh, uh, something from biological. So here, the main point is not about activation functions, but is more about the connections. So now, so as you show you before, seems that if you use original reservoir computing, the activation function is not so important. More important is the connections. And here I try to understand if it's possible to use, instead of any possible activation function, take the activation function for biology in order to in the reservoir, okay? And why? But because we want to reproduce some biological global phenomena, okay? I don't know if it's clear, but if you use reservoir computing, I am not an expert, but if you use a typical reservoir computing, there is no suggestion about the activation functions. But I want to introduce this detail from biology inside the reservoir, okay? Okay. So there is no suggestion to biology. I want to receive suggestion from biology.
Thank you, sir. So to extend to that question, sir, so in the activation function in neural networks, we have either a sigmoidal function or a tanh function being introduced. The most recent is the ReLU function. The same was explained as the reservoir function here. So there you defined a set of dynamical equations, or for example, in the case you showed as an alkaline, I think it was an alkaline which you showed in the set of slides. So can we showcase something like that in the case of neural networks also?
Okay. Yeah, I know the case here. Okay, yes. I know I cannot show you here, but okay. I think that possibility. Okay. And here I try to use. I come back. I try to use this form of this following form. Okay, sorry. The following form for reservoir here by using differential equations. Not map, but differential equations here. And here, instead of, okay, here there is some Fi, and usually Fi is, as you can imagine, can be tangent, parabolic tangent, sigmoidal tangent. Okay, I want to consider instead of that different FMY. I don't want to use the classical function used in neural networks, but I want to introduce something which is related to the dynamics of real neuron, or simplified, reduced neurons. Okay, this is all. So I want to receive from biology. Okay. And if you want, then it's possible to consider for the neural networks also for the original or reservoir computing instead of tangent. It's possible to use this kind of things, but I don't know if it's useful. I don't know if there is results about that. Okay.
Okay, sir.